In this video, we look at how Newton's experimental law of restitution can be applied to collisions in one dimension. Now, in general, the conservation of momentum does not give us enough information to determine velocities after a collision from the velocities before the collision. We usually need some further information. And this usually comes from an experimental law discovered by Newton, which is known as Newton's experimental law of restitution. And this says that for two given bodies in collision, the ratio of the speed of separation of the bodies to the speed of approach of the bodies is a constant. And this constant is called the coefficient of restitution of the two bodies, and it simply depends on the materials that the two bodies are made of. In terms of finding the coefficient of restitution, this will be done experimentally. So if we wish to find the coefficient of restitution between a ball and a surface, we could drop the ball from a height capital H above the surface, and then, provided we've got some sort of sensor that will record the upward velocity of the ball as it passes vertically up above the sensor, then we can obtain the coefficient of restitution. So if we were to drop the ball, and if we allow u1 to be the speed which the ball hits the surface, then the constant acceleration equations v squared equals u squared plus 2as will give me u1 squared equals 0 squared plus 2gh. In other words, u1 squared is going to be 2gh. So u1 is the square root of 2gh. Now, if u2 is the speed of the ball immediately after it hits the surface, and the ball is observed to pass the sensor situated height h above the surface with an upward speed of v, then the constant acceleration equation v squared equals u squared plus 2as applied in an upwards direction gives me v squared equals u2 squared minus 2gh. In other words, we've got u2 is the square root of v squared plus 2gh. Now, the coefficient of restitution is the ratio of the speed of separation to the speed of approach. So that is the ratio u2 divided by u1, which is the square root of v squared plus 2g times little h, divided by the square root of 2g times big H, and we can tidy that up as simply being the square root of v squared plus 2g little h divided by 2g big H. Now, the table here gives us some typical values for different types of balls bouncing against a steel surface and a wooden surface. So, for instance, a table tennis ball against a steel surface has a coefficient of restitution of 0.79, but against a wooden surface has a coefficient of restitution of 0.75. As a general rule, the coefficient of restitution is usually given the symbol E. So we've got E is the speed of separation divided by the speed of approach. If we've got a collision in which before the collision the grey ball has a velocity to the right of u1 and the black ball has a velocity to the right of u2, then if the collision is to occur, u1 must clearly be bigger than u2. So the speed of approach in this case must be u1 minus u2. If after the collision the grey ball has a velocity of v1 to the right and the black ball has a velocity of v2 to the right, then the speed of separation will be v2 minus v1, because v2 must clearly be a bigger number than v1, because otherwise the grey ball is going to have to pass through the black ball, which is physically impossible. So the speed of separation is v2 minus v1. If on the other hand we have a head-on collision where the grey ball is moving to the right with speed u1 and the black ball is moving to the left with speed u2, then the speed of approach of the two balls in this case is u1 plus u2. And after the collision, the grey ball is moving to the right with speed v1 and the black ball is moving to the right with speed v2, then the speed of separation must be v2 minus v1. Now these two examples ought to make it clear that in order to apply the coefficient of restitution equations, we need clear before and after diagrams. Now we noticed that when we were applying conservation of momentum in the previous video. It's just as important when we are applying coefficient of restitution. Finally, notice that if E is 1, then we say that the collision is perfectly elastic, and on the other hand, if E is 0, then the collision is said to be perfectly inelastic. So let's move and have a look at some examples. In the first case, we're just simply going to work out the value of the coefficient of restitution from the diagrams that we've been given. So in this first diagram, we have a speed of approach. Well, the blue ball is moving to the right at 8 meters per second, the red ball is moving to the right at 2 meters per second, so the speed of approach for the two balls is 6 meters per second. And after the collision, the red ball is moving to the right at 5 meters per second, the blue ball is moving to the right at 3 meters per second, so the speed of separation is only 2 meters per second. So we've got E is 2 over 6, in other words, a third. Now here are two more examples, and what I'd like you to do is just briefly pause the video and work out the value of the coefficient of restitution in each of these two examples. Okay then, I hope you've had a go at those two examples now. In the first case, the speed of approach is 10 meters per second, the speed of separation is 5 meters per second, so we've got E is 5 over 10, which is a half. In the second example, we have a speed of approach of 8 meters per second, a speed of separation of 3 meters per second, so we have E is 3 divided by 8. So let's now apply the coefficient of restitution together with the conservation of momentum to some real collision examples. So for our first example, we have two particles P and Q of masses 5 kilograms and 3 kilograms respectively, moving along the same straight line, and they collide with speeds of 4 meters per second and 2 meters per second in opposite directions. We're told that the coefficient of restitution between the particles is 0.8. We have to find the speed and the direction of the motion of the particles immediately after the collision. We need to find the kinetic energy lost in the collision and the magnitude and direction of the impulse acting on P during the collision. So, first thing we need is a diagram before the collision. Now, before moving to the after diagram, we need to make some observations. If we look at the before diagram, we can see that we've got a total momentum to the right of 5 times 4 plus 3 times minus 2. In other words, a total momentum of 14 kilogram meters per second. The fact that this is positive means that at least one of the particles must be moving to the right. It's impossible for P to be moving to the right and Q to be moving to the left, because that would mean P actually physically passed through Q, which is impossible. So we've got the options that either both particles move to the right, or that P moves to the left and Q moves to the right. Now, in our after diagram, we're going to show Q moving to the right with speed W and P moving to the right with speed V. If we end up with a negative answer for V, then that simply means we've got the direction of P's motion being wrong. So instead of P moving to the right, it would actually be moving to the left if the value of V comes out to be negative. Okay, so we have our before diagram, we have our after diagram. We can now apply the conservation of momentum to the right. So initially we have momentum of 5 times 4 plus 3 times minus 2, and that must equal the total momentum after the collision, which is going to be 5 times V plus 3 times W. So we have the equation 5V plus 3W equals 14. Now if we set up the coefficient of restitution equation, we have 0.8 is the coefficient of restitution, which is the speed of separation divided by the speed of approach. The speed of approach before the collision is 6 meters per second. The speed of separation after the collision is W minus V. So we've got W minus V must equal 4.8. So we have a pair of simultaneous equations, 5V plus 3W equals 14, minus V plus W equals 4.8. So solving those either in a traditional algebraic way or using your calculator, we end up with V equals minus 0.05 and W equals 4.75. So if we decide that the positive direction is the direction of P's initial motion, then after the impact, Q is moving with speed 4.75 in the positive direction and P is moving at 0.05 meters per second in the negative direction. To answer part 2, we need to remember that the kinetic energy of a particle of mass m kilograms moving with speed v meters per second is a half mv squared. So, before the collision, the kinetic energy that we've got for P is a half times 5 times 4 squared. The kinetic energy that we've got for Q is a half times 3 times 2 squared. So we've got an initial kinetic energy of 46 joules. After the collision, the kinetic energy of P is a half times 5 times 0.05 squared, because we're squaring it, it doesn't matter whether we include the minus or not. And the kinetic energy of Q is a half times 3 times 4.75 squared, which gives us a total final kinetic energy of 33.85 joules. So the energy that has been lost in the kinetic energy that's been lost in the course of the collision is 46 take away 33.85, which is 12.15 joules. Where's that energy gone? Well, almost certainly in the course of the collision some sound will have been created, and also there will have been some heat energy, and these will probably explain the loss in the kinetic energy. Finally, we need to consider the magnitude and direction of the impulse acting on P during the collision. So, if we show what is happening to P before the collision, it is moving at 4 meters per second to the right. After the collision, during the collision, it receives an impulse to the left, which we'll say that that impulse is of size I. And after the collision, it's moving 0.05 meters per second to the left. So if we apply impulse equals change in momentum, and we'll apply that to the left in this case, we have got I equals the final momentum to the left, that is 5 times 0.05, minus the initial momentum to the left, which is 5 times -4. So altogether we've got I is 20.25 Newton seconds. And the direction of this impulse is in the opposite direction to the initial velocity of P. Moving to our second example, we have two particles A and B of mass m kilograms and 2m kilograms respectively. They are free to move on a smooth horizontal plane. B is initially at rest and A is projected with velocity u to strike B directly. B then moves across the plane and collides with their vertical wall, which is perpendicular to the direction of motion of the particles. The coefficient of restitution between the particles is 2/3, and the coefficient of restitution between B and the wall is 1/6. We have to determine the velocity of each particle after the first impact, and the impulse experienced by B when it hits the wall. And finally, we have to describe the subsequent motion of the particles A and B. So, looking at the first impact to begin with between A and B, before that first impact we have A moving towards B with speed u. After that impact we'll have B moving towards the wall with speed v2. We're not sure about the direction of A. It may be moving towards the wall or it may be moving away from the wall. In our diagram we'll put it moving towards the wall. If v1 ends up being negative, then that simply means that A is moving away from the wall rather than towards the wall. If we now apply conservation of momentum to the right, then we have before the impact m times u. After the impact we have m times v1 plus 2m times v2. So we've got u must equal v1 plus 2v2. So there's our first equation. If we now apply the coefficient of restitution, then we've got 2/3 is the coefficient of restitution, which is the ratio of the speed of separation to the speed of approach. The speed of approach is u meters per second, the speed of separation is v2 minus v1. So we've got v2 minus v1 divided by u is equal to 2/3. So we've got V2 minus V1 must equal 2/3 u. Adding those two equations will eliminate V1, and that will give me 3V2 equals 5/3 u. In other words, V2 is 5/9 u. If we then substitute that in to equation 2, that gives me 5/9 u minus V1 must equal 2/3 u, which means that V1 must be equal to minus 1/9 u. So after this first impact, we have A moving away from the wall with speed 1/9 u, and B moving towards the wall with speed 5/9 u. So, just before B's impact with the wall, it's moving towards the wall with speed 5u/9. During B's impact with the wall, it's going to experience an impulse, call it J, acting to the left. And after B's impact with the wall, it will be moving away from the wall with a speed of W. Now, for the impact between B and the wall, if we take the restitution equation first, we have got 1/6 is the speed of separation of B from the wall, which is just W, divided by the speed of approach of B to the wall, which is 5u/9. So I've got W is 5u divided by 54. I can now use the impulse equals change in momentum equation. So I've got impulse is the final momentum minus the initial momentum. I'll apply this equation to the left because that's the direction of J. So I have got J equals 2mw, that's the final momentum of B after the impact with the wall, minus the initial momentum of B before the impact of the wall, which is 2m times minus 5u/9. And that altogether gives me 10mu/54, because I know that W is 5u/54, plus 10mu/9, which altogether gives me 35mu divided by 27. Now, after B's collision with the wall, B is moving to the left with a speed of 5u/54. A is moving to the left with a speed of u/9, and u/9 is the same thing as 6u divided by 54. So the speed of A to the left is greater than the speed of B to the left, so we can be quite certain that there are no further collisions between A and B. For our next example, we have a ball of mass 0.4 kilograms moves directly towards a wall with speed 3 meters per second. During the impact with the ball experiences an impulse of 2.16 newton seconds. We have to find the coefficient of restitution between the ball and the wall. So there's our diagram just before the impact. Here's the diagram during the impact with the wall, and here is the diagram just after the impact with the wall. So we can apply impulse equals change in momentum. We'll apply this to the left because that's the direction the impulse is acting in. So we've got the impulse, that's 2.16, equals the final momentum, which is 0.4 times W, minus the initial momentum, which is 0.4 times minus 3, because before the impact the ball is moving in the direction towards the wall, that is to the right, and we are treating to the left as being our positive direction. So we've got 2.16 equals 0.4 W minus 0.4 times minus 3. That gives me 0.96 equals 0.4 W. In other words, W is 2.4 meters per second. And now we can say that the coefficient of restitution, E, is the ratio of the speed of separation to the speed of approach. The speed of separation is 2.4 meters per second. The speed of approach is 3 meters per second. So we have E is 2.4 divided by 3, which is 0.8. Okay, at this stage it would be a good idea if you can just pause the video and have a go at these questions. And when you've done that, you've actually finished the work on this second video on collisions.